On the morning of July 1st, 2025, an automated telescope in Hawaii flagged something that shouldn't have been there. Not a star, not an asteroid. A faint smudge of light, moving against the background of the ecliptic, carrying a velocity that didn't belong to anything gravitationally bound to our sun. Within hours, orbital calculators returned the same impossible answer. Hyperbolic trajectory. Unbound. Interstellar. The third confirmed visitor from beyond the solar veil, designated 3 Atlas, had already crossed into our neighborhood, and by the time we noticed, it was already leaving. But leaving is not the same as gone, because 3 months later, as autumn deepened across Earth's northern hemisphere, the object began to move into a different kind of attention. Not because it was coming closer, it never would, but because it was approaching Jupiter. And Jupiter, in the architecture of planetary science, is not just a world. It is a proving ground, a gravitational amplifier, a place where the geometry of light and shadow, the pressure of charged particles, and the slow algebra of orbital mechanics can reveal behaviors that were invisible before. Behaviors that, in the case of 3 Atlas, had already begun to look, just slightly, unusual. Scientists don't use that word lightly. Unusual doesn't mean alien. It doesn't mean impossible. It means the data and the models aren't lining up the way they should. It means something is happening that we don't yet understand. Something that might be ordinary physics wearing an unfamiliar face, or something that genuinely challenges what we thought we knew about how interstellar objects behave when they pass through the crowded architecture of another star's planetary system. And so, as winter turned toward spring in the year 2026, a quiet but coordinated watch began. Telescopes across 6 continents and in orbit, photometric campaigns, spectroscopic windows, astrometric precision down to the milliarc second. All of them pointed at a single fading speck of light, moving silently through the space between Mars and Jupiter, waiting to see if it would do whatever it is again. If you find yourself drawn to mysteries like this, where the unknown is approached not with certainty, but with patience and rigor, subscribe now. This is Beyond the Solar Veil, and the story of 3 Atlas is just beginning. Building truth from light is not a simple thing. A single image tells you almost nothing. A position on the sky is just 2 numbers, right ascension and declination, frozen in time. But string together enough of those positions, taken across weeks and months, by different instruments in different hemispheres under different seeing conditions, and slowly, an orbit begins to emerge. Not guessed, not assumed, calculated, through the patient application of Newtonian gravity and relativistic corrections, and the subtle perturbations of every planet whose mass might tug, even slightly, on the visitor's path. For 3 Atlas, that process began with Atlas itself, the Asteroid Terrestrial Impact Last Alert System, a pair of wide-field survey telescopes designed to catch things that move. Fast cadence, automated detection, a pipeline built to flag anything that doesn't match the catalog of known objects. On July 1st, it flagged this one. But discovery is only the beginning. Within days, archival searches turned up earlier images, pre-discovery detections, buried in survey data from late June, sometimes even earlier, that had been overlooked because the object was faint and the signal weak. Each recovery extends the observational arc. Each additional night of data tightens the orbital fit, and each improvement in the fit changes the error bars on everything else: velocity, eccentricity, the precise moment it crossed the ecliptic plane. 3 weeks after discovery, on July 21st, the Hubble Space Telescope turned its aperture toward the coordinates. Not because 3 Atlas was spectacular, it wasn't, but because Hubble, even in its aging years, still offers something ground-based observatories cannot: the absence of atmosphere. No turbulence, no air glow, no weather. Just clean, diffraction-limited light. The image it returned showed a faint, diffuse coma, a cocoon of dust, surrounding a nucleus too small to resolve directly, but large enough to constrain. Models suggested a diameter between 1 and 3 kilometers, depending on albedo and activity level. The dust distribution was asymmetric, which implied jets. Localized venting. A surface that was not uniform, but patchy, responding to sunlight in ways that depended on rotation and composition and thermal inertia. That image became a reference point. A snapshot of what the object looked like at one moment, under one set of conditions. But science doesn't rest on single snapshots. It builds ensembles. Multi-band photometry from ground-based networks. Subaru, Gemini, the European Southern Observatory, added color information. Red versus blue. Dust grain size distribution. Scattering efficiency. Each filter is a question. Each wavelength is a hypothesis. JGUS, still operational and occasionally available for fast response targets, was positioned to capture thermal emission in the mid-infrared heat signature, not reflected light, which could distinguish between bare rock and volatile-rich ice, between compact grains and fluffy aggregates. ALMA, the Atacama Large Millimeter Array, stood ready to attempt spectroscopic detection of molecules, carbon monoxide, hydrogen cyanide, methanol, if the geometry allowed and the signal was strong enough. Even the amateur astronomy community played a role. Small telescopes, modest apertures, but disciplined technique. Calibrated photometry. Fits, file discipline. Time series stacks that could catch short-lived brightenings, outbursts, surges, whatever you want to call them, that the big observatories with their competitive proposal schedules and narrow observing windows might miss entirely. Science is not a hierarchy. It's a network. And in that network, consistency matters more than size. As 3I Atlas moved deeper into the inner solar system, the cadence of observation increased. Not because anyone expected it to hit anything. It wouldn't, but because the question had shifted. From what is it, to how does it behave when the environment changes? And the environment was about to change. Because ahead, massive and magnetic, lay Jupiter. Comets are not inert. They are not simply frozen rocks drifting through the void. They are dynamic, reactive, thermally complex objects that respond to sunlight in ways that depend on composition, structure, and history. When a comet approaches the sun, solar radiation heats its surface. Ice sublimates, turns directly from solid to gas without passing through a liquid phase. Water ice, carbon dioxide ice, carbon monoxide ice, each with its own sublimation temperature. The gas escapes, and as it does, it drags dust with it. Small grains, micron-sized, lifted by the pressure of expanding vapor and carried outward into a cloud we call the coma. The coma is not an atmosphere. It has no boundary. It simply thins with distance until the density becomes indistinguishable from the background solar wind. This process, sublimation-driven mass loss, is well understood. Predictable. Models exist. They account for heliocentric distance, rotation period, thermal inertia, albedo, and the angle of illumination. They predict brightness curves, dust production rates, gas emission lines. And for most comets, most of the time, the models work. The predictions match the observations, but not always perfectly. Because comets are not uniform. Their surfaces are not smooth. Jets form. Localized vents open where ice is exposed, while other regions remain dormant, blanketed by a lag deposit of refractory dust too heavy to be lifted. These jets produce anisotropic outgassing, uneven thrust, which can alter the comet's trajectory in ways gravity alone cannot explain. These are called non-gravitational accelerations. They are real, measurable, included in orbit fits as free parameters. For 3I Atlas, the timeline matters. The object passed perihelion, the closest point to the Sun in its trajectory, around October 30th, 2025, at a distance of roughly 1.4 astronomical units. Not close by any human standard. About the distance between the Sun and Mars. But close enough. Close enough that sunlight, concentrated and persistent, could drive classic comet activity even without a near-Earth approach. And the observations confirmed it. Dust, Dew. Gas, Betty. A growing coma. Brightness increasing as expected. Everything, at that stage, looked normal. But normal is a baseline, not a ceiling. Because comets also interact with the solar wind. The stream of charged particles flowing outward from the sun at hundreds of kilometers per second. When that wind encounters the coma, it ionizes the gas, stripping electrons and creating a plasma. That plasma responds to magnetic fields. It forms a tail, the ion tail, that points directly away from the sun, regardless of the comet's motion. Meanwhile, the dust, uncharged but lightweight, is pushed by radiation pressure. It forms a separate tail, curved, lagging, following the comet's orbital path. Two tails. Two physics systems. One object. This is the toolkit. The set of processes we expect. The vocabulary we use to describe comet behavior. And it works. For every comet we've studied in detail, Halley, Hale-Bopp, Churyumov-Gerasimenko, Lovejoy, it works. But 3I Atlas is not from here. It formed around a different star. It spent billions of years in a different radiation environment, exposed to different cosmic ray flux, different thermal cycling, different chemistry. And so the assumption that it will behave exactly like a solar system comet is just that, an assumption. One we test by watching what happens when the environment changes. Pause. Tension rises, subtly. Wind in E. Anomaly is a dangerous word. It suggests something broken, something wrong. But in science, an anomaly is simply a discrepancy between expectation and observation, a residual that doesn't go away when you refine the model. It's not proof of anything. It's a signal that your understanding is incomplete. The question is whether the incompleteness is trivial, an overlooked detail, a calibration error, a misunderstood geometry, or whether it points to something genuinely new. In the case of 3 Atlas, the first hints came from photometry. Brightness measurements, taken over multiple nights by independent observers, began to show scatter. Not random noise. Systematic disagreement. Some reported brightening events, sharp increases in apparent magnitude, that didn't correlate with heliocentric distance or phase angle. Others saw nothing unusual. The differences weren't huge. A few tenths of a magnitude. But they were persistent, and they didn't resolve when the observers compared notes. Aperture choice was the first suspect. Photometry depends on how much sky you include around the target. Too small, and you miss the extended coma. Too large, and you contaminate the measurement with background stars or gradients. Different teams used different apertures. Some corrected for that. Some didn't. When you reprocess the data with consistent methods, some of the disagreement goes away. But not all of it. Some of the brightening events survived the corrections. They appeared in multiple datasets, taken with different instruments, using different filters. That's harder to dismiss. Then, there was the tail geometry. The ion tail, according to theory, should point away from the sun. Always. The dust tail should lag, curved by the comet's motion. But in certain images, the angle looked wrong. Not wildly wrong. Just off. By a few degrees. Enough that you couldn't ignore it. Enough that you had to ask, is this viewing geometry? Is it a localized jet that's temporarily distorting the coma? Or is it something else? Orbit fits added another layer. As the astrometric precision improved, more data, longer arc, better calibration, the models for non-gravitational acceleration had to be updated. That's normal. That's expected. But some of the updates didn't converge the way they should. The residuals, differences between predicted and observed positions, didn't shrink smoothly. They jumped. They changed sign. They suggested forces that varied in magnitude and direction over timescales, too short to be explained by simple outgassing. And then there was the silence. Multiple teams, using sensitive radio telescopes, had conducted searches for narrow-band signals, technosignatures, in the language of SETI. Not because anyone seriously expected to find them, but because the protocol exists. When you discover an interstellar object, you check. The searches were thorough. high sensitivity, wide frequency coverage, and they found nothing. No artificial transmitters, no coherent signals, just the faint thermal hiss of dust and gas. That result is important. Not because it rules out extraordinary explanations. It doesn't, not entirely, but because it sets a boundary. It says, if something unusual is happening, it's not shouting. It's not obvious. It's subtle, embedded in the physics we're still learning to read. Jupiter, in this context, becomes a test, a natural experiment. Because as 3 Atlas approaches the giant planet, the environment changes. The solar wind is still there, but so is Jupiter's magnetosphere, a vast, rotating bubble of charged particles, trapped by the planet's magnetic field and whipped into radiation belts that glow in radio and ultraviolet. The geometry changes too. The angle between the Sun, the comet, and Earth shifts. Phase angle increases. Illumination conditions evolve. And if the anomalies are real, if they're driven by physics, not measurement error, then they should respond. They should repeat, or amplify, or change in predictable ways. And if they don't, if they disappear, then maybe they were never real to begin with. Explanations are layered. Science doesn't leap to the exotic. It climbs. It starts with the most ordinary mechanisms and tests them until they break. Only then does it move to the next rung. Tier 1 is uneven outgassing. Seasonal jets. Localized venting, driven by surface topography or compositional heterogeneity. A comet nucleus is not a sphere. It's irregular, lumpy. Some regions face the sun longer. Some warm faster. Some contain pockets of volatile rich ice, carbon monoxide for example, that sublimate at temperatures higher than water, producing activity even at large distances, where water ice remains frozen. These jets can be intermittent. They can turn on and off as the nucleus rotates. They can produce brightness surges that look sudden but are actually predictable if you know the rotation state. They can also produce non-gravitational forces that vary with time as the jet geometry changes relative to the orbital plane. Thermal lag is another candidate. Comet nuclei are poor conductors. Heat doesn't penetrate instantly. It takes time, hours, sometimes days, for warmth from the sunlit side to reach buried ice and trigger sublimation. This delay means that peak activity can occur hours after local noon, or even on the night side if the subsurface reservoir is large enough. From Earth, this looks like activity that doesn't correlate with solar illumination. It looks anomalous, but it's not. It's just thermal physics. Dust grain size matters too. Large grains fall back quickly. Small grains, submicron, respond strongly to radiation pressure and stay suspended longer. If the grain size distribution shifts, say, because a fresh vent opens and exposes fine-grained material, the scattering properties change. The coma brightens. The tail morphology shifts. The color changes. All from the same object producing the same total mass loss, just packaged differently. Fragment shedding is rarer, but documented. Comet nuclei are fragile, loosely bound. Thermal stress, rotational stress, or impact from micrometeoroids can crack them. When a fragment breaks off, it becomes its own source of activity, its own coma. If it's small and short-lived, you might see it as a brief surge in brightness, then nothing. If it's large enough, it becomes a secondary nucleus, tracked separately. But in between, in the ambiguous middle, it can look like the primary nucleus is behaving strangely. These are Tier 1. Known physics. Confirmed mechanisms. The first place you look. Tier 2 is less common, but still naturalistic. Exotic ice fractions. Carbon monoxide dominant, for example, can produce activity at distances where water ice comets are dormant. Very low-density structures, fractal aggregates, porous matrices, can have unusual thermal and mechanical properties. They can respond to radiation pressure in ways that dense, compact objects do not. They can crumble gradually, shedding mass continuously rather than in discrete outbursts. They can spin up or spin down as mass loss shifts the moment of inertia. Unusual nucleus shapes, contact binaries, elongated spindles, can produce light curves with complex periodicities that mimic changes in activity when it's really just geometry. These are Tier 2. Plausible. Testable. Requiring more data, but not requiring new physics. Tier 3 is where caution is required, where speculation meets discipline. Because if all the Tier 1 and Tier 2 explanations fail, if the observations persist, reproducible and multi-instrument, and no natural mechanism can account for them, then you're left with possibilities that sound extraordinary. Artificial origin. Technological artifacts. Propulsion-like acceleration that can't be explained by any plausible mass loss. Structured emission, coherent, patterned, repeatable, that survives independent verification. But that bar is high. Extraordinarily high. Because the history of astronomy is filled with anomalies that looked artificial until they were understood. Pulsars sounded like alien beacons until we realized they were neutron stars. Fast radio bursts looked like signals until we traced them to magnetars. The wow signal, still unexplained, taught us that a single detection means nothing without repetition. And so the rule, here and always, is this. We move only as fast as the data allows. We follow the evidence. We do not invent it. And we remain open to wonder without surrendering to certainty. The radio silence helps. Not as proof of absence, but as a constraint. It tells us that if something technological is happening, it's not broadcasting. It's not trying to be noticed. And that, in turn, limits the class of explanations that remain viable. March 2026. Mid-month. The dates are approximate. Orbital predictions carry uncertainty, but the window is known. 3 Atlas will pass within roughly 53 million kilometers of Jupiter. 0.36 astronomical units. Close, by interplanetary standards. Not close enough for tidal disruption. Not close enough for atmospheric entry. But close enough that Jupiter's gravity will measurably perturb the orbit. Close enough that the magnetospheric environment will be different from anything the comet has experienced since entering the inner solar system. Close enough that the geometry, Sun, comet, Jupiter, Earth, will shift rapidly over days, providing multiple viewing angles and phase curves and illumination conditions. This is the moment scientists are watching for. Not a single dramatic event, not a revelation, but a test, a structured, reproducible test of whether the anomalies are real. Photometry will be coordinated. Multiple observers, multiple apertures, consistent calibration. Light curves will be constructed with high time resolution. If there are brightness surges, they will be captured. If there are periodicities, rotation, precession, tumbling, they will be measured. If there are outbursts, triggered by environmental changes as the comet enters and exits Jupiter's shadow or crosses field lines in the magnetosphere, they will be documented. Morphology checks will be repeated. High-resolution imaging, looking for changes in coma shape. Geometry. Tail structure. Dust versus gas distribution. If the tail angle anomalies are real, if they're not just artifacts of viewing geometry, they should change in predictable ways as the comet moves relative to the Sun and Jupiter. If they're artifacts, they'll disappear when the geometry is corrected. Spectroscopy will be attempted during the closest approach, when the signal is strongest. Not guaranteed. Weather, scheduling, instrument availability all matter, but attempted. Looking for molecular lines, emission bands, isotopic ratios. Anything that can constrain composition and compare it to known solar system comets and to Borisov, the only other well-studied interstellar comet. Astrometry will continue, precise as ever, tracking position and velocity. Looking for changes in the non-gravitational parameters. Looking for consistency. Looking for whether the residuals grow or shrink. Because if the anomalies are real physics, if they're driven by something we haven't modeled, they should respond to the changing environment. And if they're not, if they were always just noise or misunderstood geometry, they should fade. There's also a possibility, small but real, that spacecraft assets in the Jupiter system might attempt opportunistic observations. Juno, still operational, still orbiting Jupiter, carries instruments that could, in theory, observe a transient event if the timing and geometry align. But that's speculative. The primary campaign will be ground-based and Earth orbital, coordinated. Patient.ita. Watching. Depth. What would count as unusual? Not ambiguous. Not arguable. But genuinely anomalous. A repeatable brightness jump, seen by multiple independent observers, in multiple filters, at the same time. A sustained change in coma behavior. New jets, new dust, new gas, that correlates with the Jupiter encounter, and can't be explained by solar heating alone. Or orbit residuals that worsen under every natural model, forcing the inclusion of acceleration terms that don't match any known outgassing profile. That would count. That would move the conversation. That would justify Tier 3 thinking. But until then, we watch. We measure. We wait. Interstellar objects are not curiosities. They are samples. Physical pieces of other star systems, delivered to our instruments by a gravitational accident, moving too fast to be captured but slow enough, just barely, to be studied. Each one carries information about the chemistry of distant protoplanetary disks, about the dynamics of planetary formation and ejection, about the diversity of small body populations beyond the reach of our telescope, and about how rare, or how common, objects like these might be in the vast space between stars. 3 Atlas is the third. Oumuamua was the first, strange in shape, strange in reflectance, strange in acceleration, and gone before we could learn much. Borisov was the second, unremarkable in behavior, comfortingly familiar, a comet that acted like a comet. And now this, somewhere in between. Not obviously alien, not obviously ordinary, just unclear. And that ambiguity is not a failure. It's the starting point of understanding. The facts anchor us. Discovery in July 2025, already on a hyperbolic path. Perihelion in late October, 142 astronomical units from the Sun. Never closer to Earth than 1.8 astronomical units, always beyond our orbit, always receding in one sense even as it approached Jupiter in another. A Jupiter flyby in March 2026, and then departure. Outward, into the scattered disk, past Neptune, past the Kuiper belt, back into interstellar space where it came from. We will not see it again. Not in any human lifetime. Not unless we send something after it, and we won't. So, this is the window. These months. This encounter. This careful, patient assembly of light and numbers and models and questions. This is how we learn about the universe beyond the solar veil. Not through dramatic revelations, not through contact or collision, but through discipline, through the slow construction of knowledge from imperfect data. Through the willingness to say, I don't know, and mean it, without fear, without surrender. Science doesn't kill wonder. It refines it. It shows you that the universe is stranger, more intricate, more surprising than any story you could invent. And it asks you to be patient, to withhold judgment, to follow the evidence wherever it leads, even if, especially if, it leads to an answer that is quiet and subtle and not quite what you expected. 3 Atlas is still out there, still moving, still venting gas and dust into the void, responding to sunlight and solar wind and the slow mathematics of gravity. In a few weeks it will pass Jupiter, and we will watch. Not because we expect a miracle, but because we don't know what to expect. And that not knowing, held carefully, without grasping, is the beginning of all discovery.